a blessed day, learners. Get ready and prepare yourselves as we embark on a journey of learning and enjoyment in this video. Today, we will be studying physical science through the Let Reviewer with 10 questions in set 7b. Stay safe, and may God bless you always. Welcome to the Teacher Lumaban YouTube channel.
Commit your way to the Lord, trust also in him, and he shall bring it to pass. Psalm 37 verse 5. According to the quantum theory of light, the energy of light is carried in discrete unit called A. Alpha particles, B. Photoelectrons, C. Photons, D. Protons. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, C. Photons. Explanation of each choice. A. Alpha particles. Alpha particles are helium nuclei composed of 2 protons and 2 neutrons. They are a type of ionizing radiation emitted in nuclear decay, not related to how light carries energy. Crossmark incorrect because they are not associated with light energy in quantum theory. B. Photoelectrons. Photoelectrons are electrons ejected from a metal surface when light hits it, photoelectric effect. They are the result of light's interaction with matter, not the carrier of light energy itself. Crossmark incorrect because they are a consequence of light's energy, not the energy carriers. See photons white heavy check mark. According to quantum theory, light consists of discrete packets of energy called photons. Each photon carries energy proportional to its frequency. E equals hf. Where E equals energy, h equals Planck's constant, f equals frequency. White heavy check mark correct because photons are the fundamental quantum particles of light. D. Protons. Protons are positively charged particles found in the nucleus of atoms. They are not related to the quantum theory of light or the transmission of light energy. Crossmark incorrect because they play no role in carrying light energy. Rutherford observed that most of the alpha particles directed at a metallic foil appear to pass through unhindered, with only a few deflected at large angles. What did he conclude? A. Atoms can easily absorb and re-emit alpha particles. B. Atoms consist mainly of empty space and have small, dense nuclei. C. Alpha particles behave like waves when they interact with atom. D. Atoms have most of their mass distributed loosely in an electron cloud. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, B. Atoms consist mainly of empty space and have small, dense nuclei. Explanation of each choice. A. Atoms can easily absorb and re-emit alpha particles. Crossmark incorrect. Rutherford's experiment showed that alpha particles mostly passed through the foil, not that they were absorbed and re-emitted. Absorption and emission involve changes in energy levels, not deflection patterns as observed in the experiment. B. Atoms consist mainly of empty space and have small, dense nuclei. White heavy check mark. White heavy check mark correct. Rutherford's gold foil experiment revealed that most alpha particles pass straight through, meaning most of the atom is empty space. A small number were deflected at large angles, implying they had hit something dense and positively charged the nucleus. This led to the nuclear model of the atom, replacing the plum pudding model. C. Alpha particles behave like waves when they interact with atom. Crossmark incorrect. This is more aligned with quantum mechanics and wave-particle duality, but Rutherford's experiment interpreted alpha particles as classical particles, not waves. D. Atoms have most of their mass distributed loosely in an electron cloud. Crossmark incorrect. The mass of an atom is concentrated in the nucleus, not in the electron cloud, which is diffuse and low in mass. When an electron changes from a higher energy to a lower energy state within an atom, a quantum of energy is A. Absorbed, B. Emitted, C. Fissioned, D. Fused. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, B. Emitted. Explanation of each choice. A. Absorbed. Crossmark incorrect. Energy is absorbed when an electron moves from a lower energy level to a higher one. In this question, the electron is going from higher to lower, so absorption does not occur. B. Emitted. White heavy check mark. White heavy check mark correct. When an electron drops from a higher energy level to a lower one, it releases a quantum of energy in the form of a photon, light. This is the basis for atomic emission spectra and is described by quantum theory. See fissioned. Crossmark incorrect. Fission refers to the splitting of atomic nuclei, which is a nuclear process, not related to electron transitions. Diffused. Crossmark incorrect. Fusion is the joining of atomic nuclei, another nuclear process, not involved in electron energy level changes. When does nuclear fission occur? A. When we cut nuclei into two with a very small cutting device. B. When one nucleus bumps into another causing a chain reaction. C. When a nucleus divides spontaneously, with no apparent reason. D. When electrical force inside a nucleus overpowers forces. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, D. When electrical force inside a nucleus overpowers forces. Explanation of each choice. A. When we cut nuclei into two with a very small cutting device. Crossmark incorrect. This is a misconception. Nuclei are not cut mechanically, fission occurs due to nuclear forces, not by tools. B. When one nucleus bumps into another causing a chain reaction. Crossmark incorrect. This mixes up cause and effect. A chain reaction occurs after fission starts, typically because neutrons released during one fission trigger others. But fission doesn't occur just from a bump between nuclei. See when a nucleus divides spontaneously, with no apparent reason. Crossmark incorrect. This describes spontaneous fission, which is rare and not the common way fission is initiated, usually done by neutron bombardment. Also, it's not really no apparent reason. Quantum physics can explain it. D. When electrical force inside a nucleus overpowers forces. White heavy check mark. White heavy check mark correct. Nuclear fission occurs when the repulsive electrical forces, between positively charged protons, overcome the strong nuclear force that holds the nucleus together. This usually happens when a heavy nucleus, like uranium-235, absorbs a neutron, becomes unstable, and splits into smaller nuclei, releasing energy and more neutrons. When does nuclear fusion release energy? A. When uranium emits a neutron. B. When heavy ions fuse together. C. When very light nuclei fuse together. D. When uranium splits into two fragments. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, C. When very light nuclei fuse together. Explanation of each choice. A. When uranium emits a neutron. Crossmark incorrect, this is related to nuclear fission, not fusion. The emission of a neutron from uranium typically starts a fission reaction, not fusion. B. When heavy ions fuse together. Crossmark incorrect, heavy ions are much harder to fuse due to stronger electrostatic repulsion. Fusion involving heavy ions requires much more energy and often doesn't release energy, it may consume it. C. When very light nuclei fuse together. White heavy check mark. White heavy check mark correct, nuclear fusion releases energy when very light nuclei, like hydrogen isotopes, example deuterium and tritium, combine to form a heavier nucleus, like helium. This is how the sun and stars produce energy. The mass of the resulting nucleus is slightly less than the total mass of the original nuclei, and this lost mass is converted into energy via Einstein's equation. E equals mc. D. When uranium splits into two fragments. Crossmark incorrect, this describes nuclear fission, not fusion. While fission also releases energy, this is not the fusion process the question is asking about. Albert Einstein's second postulate of special relativity state that the speed of light A can decrease if the speed of the observer decreases. B can increase if the speed of the observer increases. C randomly changes depending upon its original light source. D is constant regardless of the speed of the observer or the light source. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, D is constant regardless of the speed of the observer or the light source. Explanation of each choice. A can decrease if the speed of the observer decreases. Crossmark incorrect, the speed of light in a vacuum is always the same, 299,792,458 m/s, no matter how fast or slow the observer is moving. The speed of the observer does not affect the speed of light. B can increase if the speed of the observer increases. Crossmark incorrect, again, this is contrary to Einstein's theory. According to special relativity, even if the observer moves faster, the speed of light remains unchanged. C randomly changes depending upon its original light source. Crossmark incorrect, the speed of light does not depend on the motion or type of light source in a vacuum. Light from a moving or stationary source will still travel at the same speed. D is constant regardless of the speed of the observer or the light source. White heavy check mark. White heavy check mark correct, this is Einstein's second postulate of special relativity. It states that the speed of light in a vacuum is the same for all observers, regardless of their relative motion or the motion of the source. A passenger train travels east at high speed. One passenger is located at the east side of one car, another is located at the west side of that car. In the train's frame, these two passengers glance up the same time. In the Earth's frame, A. They glance up simultaneously. B. The passengers glance sideways. C. The passenger at the east side glances up first. D. The passenger at the west side glances up first. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, D. The passenger at the west side glances up first. Explanation. This question is based on Einstein's theory of special relativity, specifically the relativity of simultaneity, the idea that events that are simultaneous in one frame of reference may not be simultaneous in another moving frame. In the train's frame of reference, both passengers glance up at the same time. However, from the Earth's frame of reference, the train is moving eastward. To an observer on Earth, the east side passenger is moving toward where the glancing up event will happen. The west side passenger is moving away from it. Due to the finite speed of light and the movement of the train, an observer on Earth will conclude that the west side passenger glances up slightly earlier than the east side passenger. Why D is correct? According to special relativity, if two events are simultaneous in the moving frame, the train, they will not be simultaneous in the stationary frame, Earth, unless they occur at the same location. Since the passengers are at different positions, and the train is moving, simultaneity does not hold in the Earth's frame, hence, D is correct. Binet 11 travels at high speed from Earth to the star Alpha Centauri, which 4 light-years away. Which one is correct in Binet 11's frame? A. The clocks on Earth and on Alpha Centauri are synchronized. B. The trip takes more time than it does in the Earth's frame. C. Binet 11 travels to Alpha Centauri over a length that is shorter than 4 light-years. D. Alpha Centauri travels to Binet 11 over a length that is shorter than 4 light-years. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, C. Binet 11 travels to Alpha Centauri over a length that is shorter than 4 light-years. Explanation. This question involves special relativity, specifically the concept of length contraction, which states: in the frame of reference of an object moving at relativistic speeds, distances along the direction of motion appear shorter than they do in the rest frame. Let's analyze each choice. A. The clocks on Earth and on Alpha Centauri are synchronized. Crossmark incorrect. In Binet 11's frame, due to relativity of simultaneity, the clocks on Earth and Alpha Centauri are not synchronized. B. The trip takes more time than it does in the Earth's frame. Crossmark incorrect. In Binet 11's frame, the trip takes less time, not more. This is because of time dilation. To Earth observers, Binet 11's clock runs slower, but in Binet 11's frame, the distance is shorter, so the trip is quicker. C. Binet 11 travels to Alpha Centauri over a length that is shorter than 4 light-years. White heavy check mark. White heavy check mark correct. This is a textbook case of length contraction. In Binet 11's moving frame, the distance to Alpha Centauri contracts to less than 4 light-years, making the trip shorter in both distance and time. D. Alpha Centauri travels to Binet 11 over a length that is shorter than 4 light-years. Crossmark incorrect. While from Binet 11's perspective it appears Earth and Alpha Centauri are moving toward them, the correct relativistic description is that Binet 11 travels over a contracted distance, not that the star moves toward them in a shortened space. One clock is placed on top of a mountain and another clock is at the bottom of the mountain. Ignore the rotation of the Earth. Which clock ticks more slowly? A. They tick at the same rate. B. The one on top of the mountain. C. The one at the bottom of the mountain. D. Cannot be determined. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, C, the one at the bottom of the mountain. Explanation. This is a question about gravitational time dilation, which comes from Einstein's general theory of relativity. Key concept. The stronger the gravitational field, the slower time passes. Clocks deeper in a gravitational well, closer to a massive object like Earth's center, tick more slowly than clocks at higher altitudes. Analysis of choices. A. They tick at the same rate. Crossmark incorrect, time does not tick at the same rate when clocks are at different gravitational potentials. B. The one on top of the mountain. Crossmark incorrect, the clock on top actually ticks faster, not slower, because it is in a weaker gravitational field. C, the one at the bottom of the mountain. White heavy check mark. White heavy check mark correct, it is closer to the center of the Earth, where gravity is stronger, so time passes more slowly there compared to the top. D cannot be determined. Crossmark incorrect, this is a well-tested and measurable effect, it can be determined. You are in a windowless spacecraft. What do you need to do to determine whether your spaceship is moving at constant non-zero velocity, or is at rest, in an inertial frame of Earth? A. Make very precise time measurements. B. Make very precise mass measurements. C. Make very precise length and time measurements. D. Nothing, because you cannot succeed no matter what you do. In the next 5 seconds, select the best response from the available options. 5, 4, 3, 2, 1. Correct answer, D. Nothing, because you cannot succeed no matter what you do. Explanation. This question tests your understanding of Einstein's first postulate of special relativity, also called the principle of relativity, which states: the laws of physics are the same in all inertial frames of reference. Therefore, there is no experiment you can perform inside a closed, windowless, system to determine whether you are at rest or moving at a constant velocity. Breakdown of the choices. A. Make very precise time measurements. Crossmark incorrect, time measurements won't help because clocks behave the same in all inertial frames moving at constant velocity. B. Make very precise mass measurements. Crossmark incorrect, mass doesn't change in a detectable way inside the ship if you're moving at constant velocity, it only appears different from another frame. C. Make very precise length and time measurements. Crossmark incorrect, even these won't allow you to detect constant motion without an outside frame of reference. D. Nothing, because you cannot succeed no matter what you do. White heavy check mark. White heavy check mark correct, this aligns perfectly with special relativity. If your motion is constant and not accelerating, you're in an inertial frame, and there's no internal experiment that can reveal whether you're at rest or moving uniformly. I can do all things through Christ who strengthens me. Philippians 4 verse 13.
I hope you enjoyed and learned something new from our topic on physical science. Lead reviewer. If you learned something from this video, please give this video a thumbs up. Don't forget to share this video with your friends. If you have comments, questions, or suggestions, you can leave a message in the comment section below. Thank you very much for watching my videos. Hoping that we meet again in my next video, and God bless you always. It is the Teacher Lumaban YouTube channel.